All right, so we shall move on to the next presentation that will be presented by Paa Kwesi Bordoh from Ghana. Paa Kwesi has completed his first degree, BSc in Agricultural Technology at the University for Development Studies in Ghana. And he is currently an MSc student in our international program here at the Hebrew University. Where is that? Here it is. And Paa Kwesi will present us his seminar on the influence of hot water rinsing and brushing on tomatoes' internal and external quality. Please, Paa Kwesi.
Thank you very much. My name is Paa Kwesi Bordoh, as Prof. Saranga introduced. And the title of my presentation is The Influence of Hot Water Rinsing and Brushing on Tomatoes' Internal and External Quality. This experiment was done at the Department of Post-Harvest Science in the Agricultural Research Organization and the Volcanic Center under the supervision of Professor Fallik. Unfortunately, he's not here, so he has sent someone to sit in for him, the person of Jacob. And the order of presentation is as follows. I'm going to look at the introduction, the objectives, materials and methods, results and discussion, and the conclusion. Now, as part of the introduction, most harvested commodities need to be free of disease, insects, synthetic chemicals, and clean before they are packaged and exported. Now, the susceptibility of fresh harvested produce to post-harvest diseases increases during prolonged storage. And this disease may be as a result of physiological and pathological deterioration. And as it stands now, there is no post-harvest fungicide that have been registered for the control of decay-causing agents in tomatoes. Now, even though there are other non-chemical technologies which are also used to control decay-causing agent and also prolong the shelf life of tomatoes, some technologies, like I said earlier, have been developed, and some of which include irradiation, the use of materials that are generally regarded as safe, GRAS for short. We have hyperbaric treatment or modified atmosphere packaging. Now, all these treatments are non-chemical, and they have also proven to be a very good method or technology to control decay in tomatoes. However, heat treatment happens to be one of the promising means for post-harvest control of decay, as has been discussed by Coy and Lurie in 1989 and then 1998. Sorry. Now, heat treatment, like I said earlier on, may be applied to, not only to fruit but also to vegetables, using hot water dip, vapor heat, hot dry air, and then hot water rinsing and brushing, of which my research was all about. Now, some of the benefits of using this technology is that it's very easy to use, and the treatment time of washing the fruit is very short. And aside that also there's reliable monitoring of fruit and the water temperature, as well as very effective and efficient in killing of skin-borne decay-causing agents, which are mostly found on the skin or the peel of the fruit. Now, Lurie et al. 1998 said the optimal temperature to treat fruit before storage at 12, and the recommended storage temperature of tomatoes is 12, can maintain the quality parameters by reducing decay incidence and chilling injury. Now, to support this claim, research has been done over the years by Fallik et al. 93, 2001, and 2002. And in his research, tomatoes were exposed to a temperature of 38 degrees Celsius for 3 days. And in another experiment also, this technology was also used where the tomatoes were washed at a temperature of 52 for 15 seconds. Prior to storage. But after storage, they noticed that there was decay decay in development was inhibited without affecting the fruit quality and other parameters. And apart from alleviating certain physiological disorders, which I've mentioned earlier on, like decay and chilling injury, the heat treatment also maintains and improves the antioxidant defenses. I must also say that the tomato have a lot of antioxidants in it, like vitamin C, carotenoids, to mention but a few, but paramount among them is the vitamin C. And in an experiment which was done by Coy et al. 2006, when heat treatment was used for mushroom, raw shiitake mushroom, Latendus edudis, and at that 100 degrees and 120 for 15 and 30 minutes using autoclave before storage, they realized, or they observed, that the antioxidant activity was maintained and improved. So in this experiment, we also wanted to find out that at what temperature, that if we wash the fruit, and at what maturity stage, that if we harvest the fruit before storing, and at which storage temperature can maintain these qualities that we are talking of, as well as inhibiting decay and chilling injury. So the objective of this study was to determine the influence of hot water rinsing and brushing on tomato Solanum lycopersicum, which is also called Lycopersicum esculentum male, the external and the internal parameters of vitamin C and the total antioxidant activity, which is what we are most interested in, because the total antioxidant activity, even though has been done in tomatoes, but not with this technology. So this is the first time that this technology has been used to determine the total antioxidant activity in tomatoes after prolonged storage and marketing simulation. Now, to achieve this objective, we have this methodology. Now, the tomato fruit was harvested at 2 stages, as you can see, matured green and pink. So whenever you see pink, it's just an abbreviation of my short name, PK, without effect. And the fruit were harvested every 3 weeks for 3 to 4 months. And this experiment was repeated 3 times from commercial non-heated plastic house in the central region of Israel. Now, what we were looking at is that we wanted to look at how the heat treatment, like I said in my introduction, is able to influence, we categorize under 3, the external, the internal qualities, and the nutritional level. For the external, we're looking at the weight loss, firmness, and color, as well as decay incidence. And then the internal quality, we're looking at the titratable acidity, that is TA for short, and then the TSS, which is the total soluble solids. And then the nutritional compound, mainly vitamin C and antioxidant activity along the growing season. Now, before the heat treatment, the fruit was sorted out according to uniform color and size for the pink. And then for the matured green, it's much obvious because the green is green, you can easily see. So the green was sorted out according to its size. And then the fruit calyx were all removed. Now, the temperature that we use for our treatment was we wash the fruit at 51 and at 55 for 15 seconds, whilst the 22 served as our control. 22 is the temperature for mostly for tap water. So we wanted to see if we use tap water in relation to the heat treatment, what would be the effect. Then after the heat treatment, the fruit were then stored at 2 separate temperatures. That is for both pink and matured green, at 5 degrees centigrade and at 12 degrees centigrade for 3 weeks, plus 3 days of shelf life. And the emphasis of this was a simulation of seed transport to Europe and marketing. So in total, we had 12 treatments, and each treatment consisted of 25 fruits. Now, this is just a schematic diagram of the machine. And as you can see, the first column you see here is the conveyor. The fruits are kept here. They are conveyed into the washing chamber. The first chamber is for the control, and the third chamber is for the treatment, the heat treatment that we want to look at. Now, when this one is in operation, this one is shut down so that it doesn't have effects on the treatment. And in the heat treatment section, you can see at the bottom here, we have the hot water container. So this pump recycles the hot water, and the fruits are washed as they move along this conveyor. Now these black round things you see are the brushes. They are very soft, so as the fruits move along, they are brushed gently, and they don't have any effects on the fruit. Then they are then conveyed to the dryer, and they dried approximately at 22 degrees Celsius for some few minutes, seconds, and then they are separated or sorted out according to the storage temperature that we want. So this picture here you see, this is a clear picture of the machine. As you can see, that is me doing my own thing. That is the washing chamber. This one is for the control, and this one is for the heat treatment. And as you can see, the fruits are moving gently, and the water drops on it. It rinses, it is brushing it, and that's how the name of the machine is. It rinses, and it is what? It is brushing. So that is the name of the idea behind this technology. And then this is the dryer. Okay, so from here it goes to the dryer, and then it dries it. Now, after the heat treatment, we, like I said earlier, have to take all the parameters. Now, the parameters has to be taken in such a way that we had to destroy the fruit at a point in time. So we had the destructive and then the non-destructive. And the non-destructive basically has to do with the external qualities. So we look at the weight loss, like I said earlier, the firmness, the color, and then the decay. And for weight loss, firmness, color, we used 9 fruits representing the 9 replications. And then for the decay, we took into consideration all the 25 fruits. Now the weight loss was measured using the Sartorius electronic scale, and that is it over here. And it was calculated as the percentage weight loss from the initial weight. And then the firmness was measured using the durometer, and that's the durometer. And the durometer has no physical unit. The values were arbitral numbers. So the higher the value, the higher the firmness, and the smaller the value, the lower the firmness of the fruit. And then the color was measured using the Minolta chromometer. Higher values means higher inhibition of color, and lower values means the inhibition is very small. We will look at this when I discuss the results better. And then the decay, we considered fruit as decayed when we saw a mycelium. That is after we've taken them from storage. And for the decay, the replication was based on the number of experiments. But for each treatment, we calculate the percentage decay out of the 25 fruits. Okay. So we have the internal qualities. The internal qualities, we have 9 replicates from the external. And then for TSS, we had 9 replications. The TA also, we have 9 replications. The TSS was measured using the digital refractometer, as you can see. And then the TA was measured using the automatic titrometer. And the TA was expressed as the percentage of citric acid. Now, for the nutritional compound, that is for vitamin C, and the antioxidant activity, we had 36 treatments. Now, 36 treatment was used for the vitamin C. So the 36 treatments represented the 36 replicate. And the vitamin C in this case, which is an antioxidant in tomatoes, was expressed as the ascorbic acid content in the fruit using the ascorbic acid kit test from HANA instrument. And then the antioxidant activity was determined using DPPH solution. Actually, it is a freshly prepared diluted DPPH solution. And with this method, we had 180 replications. And each replications were put in this is what we call the cavity. So they were put in this cavity, 180 of them, and prepared for the spectrometer, the Ultra 2001 spectrophotometer, sorry. And based on that, we have a data sheet which was generated, and we use this formula to calculate the percentage of inhibition to determine the antioxidant activity, as was described by Abalaka et al. 2010. Now, my analysis was performed according to factorial design using the JAMP 8 and significance was done at 0.05% significance, and I use mostly Microsoft Excel to draw my graphs. But the data, the tables presented in this presentation was presented using the F values. I use the F values to present. All right. So now let's look at the results. Now the first result is the decay incidence. And as we can see in the decay incidence, the heat treatment at 51 and at 55 inhibited chilling injury at 5, because that's what we normally find chilling injury. And at 12, we noticed that there wasn't any decay in both pink and matured green. But when we come to 12, you notice that the pink fruit decayed, some of them decayed. And the reason we can see from this picture here that at 5, this is the pink and this is the matured green fruit. And at 5, this is a control. There was decay in the pink, and then decay also started developing in the matured green. Then also, if we look at 12, a similar situation happened. This is the pink, and then this is the matured green. And then at 55, we also had a similar situation. And this decay was actually due to the heat damage because this temperature was very high. So we believe that because of the high temperature, it might have resulted into, the decay at this temperature. So in general, we can say that these two heat treatments at 51 and at 55 significantly inhibited decay incidence. But it was more pronounced, as you can see, in 51 than in 55 for both maturity stage of the fruit. And the reason why you find the inhibition for the decay was that in the research which was done in grapefruits, they noticed that the pathogenesis-related protein, which are found on the skin of the fruit, the thermal or the heat treatment induced these proteins. So they were able to serve as a defense for the fruit to fight these pathogens. All right. Now the next slide is the weight loss. And for the weight loss, we never had any interaction between the heat treatment, the maturity stage, and the storage temperature. But we noticed that there was interaction between the maturity stage and the temperature. And as you can see, at 5, when the fruit was stored at 5, you notice that the matured green lost weight, even though there was no significant. And then at 12, we'll notice that, except in the control, but at 12, we notice that the matured green lost weight more than the pink, whereas in the other one is the other way around. So we can see from this data that these two heat treatment, even though there wasn't any significant difference between the heat treatment on the maturity stage and after storage, we believe that these heat treatments were able to reduce the weight loss, as you can see at 5, and then at 12, you can see. But in the control at 5, there was too much weight loss over here. And then for the firmness, we didn't have any interaction between the heat treatment, the storage temperature, and the maturity stage. Sorry, between the heat treatment and the storage temperature, but there was significant effect of the maturity stage. And as you can see, at 5, the storage temperature had a significant effect. And at 5, most of the fruit, you can see that the fruit were much firmer at 5, both in pink and then in the matured green. And then the the matured green was much firmer than the pink fruit. That is after storage in all the temperatures. And if we look carefully, when we did the student t-test, we noticed, even though there's no significant difference of the heat treatment, we noticed that these two treatments somehow was able to maintain the firmness of the fruit, that is at 51 and then at 55. But the recommended storage temperature, like I presented in my introduction, is 12. And as you can see, in 12, the pink you can see here was not the same, but in 51 and 55 it was much higher, and we think that this heat treatment was able to maintain the firmness. And then for the color, we also noticed that for the color, the heat treatment, the maturity stage, and the storage temperature had significant effect on the color. There wasn't any interaction. And if you look at the chart here, you notice that at 5, there was significant inhibition of color, especially in the matured green, whereas for the pink, they ripened normally. And if you look at 12, both pink and then the matured green at this storage temperature, they ripened normally. But the inhibition of color was more pronounced in the matured green, especially at this temperature at 5 degrees Celsius. So we can say that these two heat treatments, that is 51 and 55, significantly inhibited the color, and then it was much pronounced at 55 than at 51 in the color. Now, when we look at the TSS, the total soluble solid, we didn't also have any three-way interactions, but we noticed that the maturity stage of fruit, the pink had a high TSS. The pink had a very high TSS, as you can see, after storage at 512. And the interaction was that at 5 degrees, you can see that even with this heat treatment, the TSS was very high in pink as well as in this heat treatment. And then at 12 also, the TSS was a little bit low under each of the treatment. Now, if we come to the control, we will realize that the TSS was very, very high. And the reason being that at this stage, most of the fruit ripened. And the TSS mostly increases according to the ripening process, as has been shown by the color development. And if we look at the vitamin C also, the vitamin C, the heat treatment didn't have any significant effect on the vitamin C. The maturity stage had significant effect on the vitamin C, but the storage temperature, we didn't see any significant effect. So you can see in the graph that this heat treatment improved the vitamin C at 5, and it was also, vitamin C was also improved at 5 for the control. So we can see here that the pink fruits were having a higher vitamin C as compared to the matured green. Now for the antioxidant activity, we also noticed that the heat treatment, the maturity stage of the fruit, and the storage temperature also had effect on the antioxidant activity. But most importantly, we noticed that most of the heat treated fruit, even though there wasn't any significant difference, but most of the heat treated fruit had a higher antioxidant activity, especially at this storage temperature, which of course was not different from in the control at 12. But in the decay, we noticed that there was decay in the control at 12, and there was some decay also at 5. So if we are considering which type of treatment you want to use, I mean, which treatment is better or something like this, then we will consider these two heat treatments, since here there wasn't any form of decay or any chilling injury. So in the antioxidant activity, this heat treatment was able to maintain or improve the antioxidant activity. All right, so this is just the table of what I have presented in most of the graphs. And in the weight loss, we didn't see any significant effect of the heat treatment. We didn't see any significant effect of the maturity stage. We didn't see any significant effect of the storage temperature, but there was interaction between the maturity stage and the temperature. And when we come to the firmness, the heat treatment didn't have any significant effect, but the maturity stage and the storage temperature had significant effect on the firmness. And when we come to the color, these three main effects had significant effect on the color, and we saw some interaction as I showed in the graphs, that the maturity stage and the temperature, there was a significant interaction. And for the decay, we also saw a significant effect of the heat treatment on decay, and we also saw significant effect of the maturity stage on the decay. And if we look at the TSS, the TA, vitamin C, and then the antioxidant activity also, is the heat treatment had effect. The maturity stage, we also had a significant effect, and we also had an interaction, a significant interaction between the heat treatment and the storage temperature. But we didn't find any significant effect of the heat treatment, the maturity stage on TA, and there wasn't any interaction for the TA. And when we come to the vitamin C also, the heat treatment didn't have any significant effect, but the maturity stage had significant effect on vitamin C. Whereas in the antioxidant activity, heat, maturity stage, and the storage temperature had effect, and there wasn't any interaction whatsoever. So in my conclusion, a combined and optimal hot water rinsing and brushing at this temperature of tomato, especially at the pink stage, and after storage plus 3 days of shelf life at this temperature, maintain the keeping qualities, that is the TSS, vitamin C, and then the antioxidant activity. Now in literature, we noticed that the TSS, the color, had somewhat a correlation, in the sense that as the fruit ripened, the total soluble solids also increases. But if the fruit doesn't ripen so much, it also have some effect also on the total soluble solid. And the vitamin C and the antioxidant activity, we noticed some kind of correlation, even though I didn't put it here, but it wasn't something that we're so much interested in about the correlation. But we noticed that as the vitamin C increased, because the vitamin C in itself is an antioxidant, so when the vitamin C was increased, especially the heat treatment at this, we also noticed that the antioxidant activity also increased, and especially at this temperature or that temperature. We also noticed this heat treatment maintained the firmness of the fruit, even though the matured green was much firmer after storage at this. And this heat treatment also maintained the ripening process of the fruit as well as for the matured green. And most of the fruit, both the pink and the matured green, they ripen normally at this storage temperature, as was shown by the color development in the graphs, the graphs that I showed. Also, we believe that this heat treatment significantly inhibited decay incidence after storage at 12, and then was able to reduce chilling injury. Now, the reduction in chilling injury is that with chilling injury, research has shown that in the peels of the fruit, there is a protein, that is the heat shock protein, and the thermal stress induces this protein, and that makes it become sort of able to resist, or be able to become resistant to chilling injury, especially at very low temperatures. So we think that this technology should also be explored on a broader range of fresh harvested commodities for minimally processed products, since it reduces the risk of health problems due to the fact that the treated fruits are devoid of chemicals. Because as you can see in this treatment, we didn't use any chemicals. We only used the water to wash the fruits. So we think that it should be explored not only in tomatoes but in other commodities. And then finally, we also think that the enhancement of the fruit tolerance to low temperature by reducing chilling injury or by enhancing fruit resistance to decay-causing agents could allow prolonged storage at temperatures which are lower than currently used. And this will increase the possibility of some commodities to be exported by less sea transport rather than by air transport. Thank you.
We're ready to take questions.
Thank you for your presentation. That was a nice one. My question is, I want to know the importance of the removal of the colors, because somewhere in the materials and methods it was mentioned that the colors of the fruit was removed before the treatment.
Okay.
And I've read somewhere or I understand that the colors prolong the shelf life of the fruit. But in this treatment, it was removed. I want to know if there's a special reason for that.
Okay. I'll explain it using this machine. The colors was removed because when the fruits are being rolled on the brushes over here, we don't want a situation whereby it will get stuck in the brushes. Or better still, because it is sharp, the color is pointed. So if they roll on the brushes, there's a tendency that the colors can even destroy the skin of the other fruits. So to avoid that, that is why we remove the fruit calyxes for this treatment.
Okay, all right. Is in your first graph of your results, it shows that at 55 Celsius, the temperature was high enough to give injury for the pink, but not to the mature green.
Yes.
And do you have an idea why is that?
Yeah. Well, I think that at this temperature, the pink, of course, was susceptible to the heat damage that caused the decay. And the matured green, of course, we didn't see any decay. And literature has shown that in the skin of the fruit or the peel, there's this pathogenesis-related protein like chitinase, which when induced by thermal stress, okay, can help to prevent any pathogen attack. So we think that this was more expressed, this gene which was responsible for producing this protein was more expressed in the matured green than in the pink. And so the heat treatment would have caused more expression of that gene in the peel to be able to induce the decay in the matured green than in the pink. Yes.
Okay, do you have any explanation, or can you speculate on how this hot water treatment enhances chilling resistance or tolerance in the fruit?
Okay. For chilling injury, some researches have been done previously, and at 51 and at 52, it's able to inhibit chilling injury, but below, when you watch the fruit at 22, we notice here that there was still some decay, which is due to the injury. And the reason why we didn't have any injury at 5, chilling injury at 5, is that there's a protein, that's a heat shock protein in the fruits, which when expressed as a result of the thermal treatment is able to inhibit the injury, especially at this temperature. So we believe that the thermal condition or the heat treatment probably might have induced this gene, which is responsible for inhibiting chilling injury, to be expressed more at heat-treated fruit, and so we're able to inhibit the chilling injury.
Thank you. Why is it important to include 51 and 55? I don't know. I don't understand why.
Okay.
Maybe either of these two temperature may be enough to test this experiment. You have a long gap between, maybe you consider 22 as a control and you have 51 and 55. I think in most of your data, there was more or less, there was no significant difference between the two, right?
Yes.
So I don't know why you included 55 and 51.
Okay. With previous research that has been done, and from literature, when fruit were washed above 55, we saw decay. But in some fruits, some varieties of tomatoes, there was inhibition of injury, and in some variety, there wasn't any inhibition of injury. And we chose 55 and 51 as our heat treatment because 52, 53 has been done. So we also wanted to see that at this temperature, is it also possible to inhibit the decay incidence as well as inhibiting chilling injury? So that is why we chose. So the idea, we washed this fruit at 51 and at 55. That's where we washed it. But in my materials and methods, I mentioned that Fallik et al. Also did a similar experiment, but it wasn't at 51. It was at 52. So 51 plus or minus 2 will not have any, will be able to inhibit decay and chilling injury. But something above 55 or 55, of course, can inhibit chilling injury, but decay, it can cause decay due to heat damage. And the reason why we use 22 is that, of course, most of us, when we go to the supermarket to buy fruits or the tomatoes, we wash them with tap water. And we assume that approximately the tap water is around 22 degrees Celsius. So by using this storage temperature, you want to see if you wash your fruit with tap water and then you put it in your fridge for some time, what is going to happen after a very long storage. So the rationale behind the 22 is we want to purge it at using tap water if you want to store your fruit.
Yeah, that's fine. 22 is fine, but 51 and 55 is not convincing to use as a separate treatment.
But there is convincing because if you look at the, of course, in the other parameters, we noticed that there were no significant differences and all that. But in the decay, and like I've shown in the, excuse me, here, of course, there wasn't any significant difference in weight loss. There wasn't the heat treatment. But if we look at the color, there was, when we did the student t-test, we noticed that there was significant difference between the heat treatment, between the heat treatment on color. And the inhibition was much higher at 55 than at 51. And one thing we should know is that color also plays a very important role in the ripening, because as fruits ripen, they change color. So the color is an indication to tell us whether the fruit is ripening and whether it's deteriorating very fast. So if we're able to inhibit color at a certain temperature, then it means that we can prolong the shelf life of the fruits. And the heat treatment was able to do that for us, especially though it matured green than in the pink.
Okay, thank you.
This one?
I don't know if I'm understanding right the graph, but you're saying that for 22 degrees after you storage them at 5 and at 12, the fruits lost more weight at 5?
Yes.
why would the fruit, and I think it is more or
Okay.
less in all of them, why would they lose more weight under lower temperatures? It's supposed to be that they wouldn't lose weight at lower temperatures.
Okay, let me start with the heat treatment at 51 and at 55. You know, at 55, when you wash the fruit at this temperature, you see if we didn't do that, but if we are taking a microscopic image of the peel of the fruit, you see some layer of wax around the peel. So this wax at this temperature was able to seal the visible openings on the peel. So that would have accounted for some reduction in this heat treatment. But of course here, there wasn't any recrystallization of the wax around the peel. Other factors could also contribute to weight loss, not only the wax, like the frequent opening of because we did it in a storage room where people were also keeping their fruit and all that. So opening and closing of the storage room can also change the atmospheric condition. I mean, temperature, relative humidity and all that. So that could have also been a reason. But here, we're looking at how this heat treatment was able to do the trick, and we noticed that there's recrystallization of some wax around the peel, which sealed the visible openings, so we're able to reduce the firmness. And it was the same thing in the weight loss and in the firmness.
Other questions, guys? Okay, if so, let us thank PK for his presentation.